So welcome back again. We are about to complete our aerosol sampling part. So this will be probably the last, and then one will be on the filters. So we will be discussing this one. So this is how the sampling system looks like. You have a kind of PM 2.5 and PM 10 sampler, like this is actually like I have already explained in the previous lecture that the air comes from here, it goes this one, and then you can imagine this is actually a particle, bigger particle is actually just deposited here, and then the smaller particles that are there in the air. So there are two particles, suppose they are coming, one is bigger, one bigger will be stacked here in the greased surface, then the remaining air will go up and then it will bounce back, and then what it comes here, and then you have kind of fan is there, are my to control the flow rate. So flow rate will be there. So when we do high volume samplers, so it depends actually. For example, you can collect actually like 1500 cubic meter of air, depending on the for example, if you are using 1 meter cube per minute, then and for 24 hours, and then in 24 hours we have actually kind of 60 minutes, 1 hour per hour. So what will be there, how much it will be there? So 0 about 1440 meter cube if it is 1, but generally it is not precisely 1, it will be sometimes 1.0 plus minus 0.1, 0.1 little bit becomes we say if your flow rate is in this range meter cube per minute, it is okay. So plus minus 10% of deviation or in the flow rate is accepted here, not too much. Beyond that one, it will be, you will have huge uncertainty in this one. So for example, even if you are using 1 meter cube per minute, and then you are giving a relaxation of 0.1 or standard deviation is 0.1, you are going to kind of have a relative standard deviation of 10%, and this 10% will be cumulated and it will go further up when you are doing the aerosol chemical composition measurements. So I have explained this one. Then once we have done the sampling, the filters are reweighed, we weigh again, and the difference between pre and post filter is calculated, and then you have a kind of actual PM measurements, that is actually microgram per meter cube. So this is very important. I think the idea is very simple, and then equations are also very simple. You can just read through this one, and then now there are actually kind of, because this there are two problems with this single one when you are doing, for example, PM10, and as I said that now we are more interested in doing fine mode aerosols because they can deeper penetrate into our lungs, so they can affect our biological system more compared to the PM10 particles. So there are the new samplers has been devised, like hybrid samplers, in which in one go you can collect PM 2.5 and PM 10. For example, in India we generally use from Envirotech, that is one of the very highly respected companies for the aerosol sampling units. So we generally use that one, and here hybrid samplers, the idea is that you can and then advantage is that you can collect PM 2.5 and PM 10 samples together, and then if you get one time, that's very good actually. And then suppose you are using another system, two different systems, there why combo sampler or hybrid samplers are actually advantageous, because here the flow rate is same. So the PM 2.5 and PM 10 flow rate, so the differences in particulate matter concentration because of the change in flow will not affect your particulate matter concentration. But if you are using two separate samplers, and suppose one sampler is having some issue, and then your mass can be actually disturbed then. So PM 2.5 to PM 10 ratio, when you calculate, that can be affected. So the air stream is in this combo sampler, the air stream is directed through a size selective inlets, whether it could be a cyclone or virtual impactor, which can separate PM 10 and PM 2.5 based on the particle size. So this is the example that is shown here. the same is actually like, you have a sampler inlet here, and you have first PM10 inlet, then you have a segregation device here, and then you will be like actually 13.67 LPM, for example, we are collecting here, and then some of the air will be going here, so that the air is bifurcated, and you can calculate based on that one. Flow measurement and control. As I said in the very first slide, our idea is to, since B is equals to Q into T, this has to be highly precise, okay, and I said that plus minus 10% error is accepted. Beyond this, we usually don't accept this one. So this means the one of the very important parameters that controls our PM concentration, because PM will be actually like m upon volume of air, m for example you put in microgram, and volume in B cube. So B cube, when you have to calculate B, you have to calculate in meter cube. Then your the very fundamental time you can measure very easily. There is no much difference, not much difference can be there in the time. But I must remember, I tell you, because suppose there is a power failure, what will happen? You said that I started at 6 AM in the morning, and there was a power failure for about say 2 hours, and you stopped your measurement at 14 hours. In principle, what you said that I have collected my sample 6 and 6:12 and 8 hours, but there was actually 2 hours there was no electricity, and in Indian or low cost PM samplers, you will not, they don't record these kind of things actually, that if the sampler was off. In Thermo Anderson sampler, that is USA, it's very expensive. They used to use actually kind of chart. So when the suppose this is the actually flow rate, so when this flow rate will be there, so if there is no kind of reduction in the flow and there is no power cut, this will complete like this. But suppose at some point of time this will be like here, and then if there is a power cut, this will suddenly come here, and then suppose then light comes, then it starts from here. So here and here you can see that how much time the power cut was there. So my suggestion to the students would be that you start your wristwatch, okay, you take time from there, and then you match your time with the sampler, okay. So when you are doing this one, you have actually two things. You have already know that actually that my wristwatch is actually correct or watch is correct. So you note down this one. So you note down with this one, and then you note down the sampling time. Sampling time actually is usually gives in meter cube. So you can calculate, or sometimes they are also given in reading is directly is given in the meter cube. Sometimes it gives in the meter. In the hours, okay. So you can calculate with this one. This kind of things are very advantageous, because if the power is off, then you can get that one. So flow measurements very important, and this means if you want to more precise, this means what you have to do, you have to kind of what you have to do, you have to calibrate your pump, okay, very regularly, not only this is important, regularly, okay. So this means when you are going to start, say in a month at least, you should calibrate your PM sampler. This will give actually a very good idea, then only you can do. So this will maintain not only the volume, but this will also maintain the size selective inlet properties, okay. And we know that in the because this air is pulled through the sampling system by the means of pump, and then if there is actually change in flow because of the deposition of the particles that on the filters, there will be a mass flow controller who will be doing their job. So they will be actually increasing and depending on the pressure drop. So that can be there. This is size selective inlets. This is actually like shown for PM 2.5. Inlet is there actually. It is a coarser ring. So you have a very bigger rings here, very big dots. Then you have a here on the other side, if you see, that is actually PM10. So the inlet actually diameter will be larger actually for PM10 compared to the inertial classifier are used to remove the particles larger than a specific diameter. So the diameter, usually the nozzle that I have shown in the previous one, nozzle size is usually same, but then inlet will be very different, cyclone and other things in that are there actually. So filter cascade in the top you can use, then you can use the collection filter, for example. Then once you have the size selective inlet, you need to put kind of filters. Usually 37 mm or 47 mm are used in kind of like when we have a kind of combo samplers and the top. Then you have a 45 mm final collection filter on which our filters, our air particles will be collected. Then you of course also need some support, otherwise your filters will go. And then in the bottom there should be actually cascade in that filters can be put this, so that this can be actually very properly fitted. So this kind of things will be there. And then in the exhaust, in the final states you can have exhaust, because the air has to be removed. Air will be removed. So once the air is removed from the system, so you need to have the exhaust in this one. So the three factors, there are few very important factors, and these are the three very important ones, like the factors that affect the particle impaction. So velocity of the air. So this is precisely important, and all the research that goes in this one, that how much actually we should keep the flow rate. Okay, so this is lots of research goes on this one. Then size of the particles, and then size of the collection body. These are the very important things. That collection body means what we say here, it's little bit confusing. So this is actually like filter. So what is the size of the particles that you are going to collect, and then size of the filter paper, that becomes very important. Okay, so little bit complicated now, but not. You just remember this one, that we said discuss in the previous lectures. We have been discussing that the PM 2.5 and PM 10 collection happens by the impactor. So what is the principle of the impactor? So in this one we have a kind of air that is actually coming, okay, and you have this airflow is accelerated through a nozzle, okay, directed at a flat plate. For example, you have a flat plate here, okay, impaction plate that is called, and you have a nozzle. If you don't have a nozzle, the velocity, you cannot increase the velocity. So just to increase the velocity, and that's why the impaction becomes very important, okay. So you increase this, you can decide the width of the nozzle. You can see in the equations there is actually this is a Stokes number. We will calculating this one, we will come to that one. So once you have airflow is actually like exhaust that is there, this is passing through this one, and then all the direction the air is coming, but there will be a nozzles. When it passes through the nozzles, this will be in principle, if this, what will happen because of this movement, this will have high what you call velocity. So what will happen in normal flow, this could have been depositing here, but when you have very high flow, it will be slightly diverted actually, okay. So the impaction place deflects flow to form a 90-degree bend in the streamline. Particles with sufficient inertia, this is very important, particles with sufficient inertia. And how will you quantify that, whether particles has the sufficient inertia or not? It is given by the Stokes number, okay, Stokes number, and that is STK, are unable to follow the streamlines and impact on the plate. So those particles who are actually having less inertia, they will not be impacting on the surface, and they will be going away from this one. So for example, this is a bigger particle, so this doesn't have a very this Stokes number, and this will be very high. So what will happen, this particle will be deposited. But when you have a particle with the smaller sizes, these smaller sizes particles will not be impacted because their Stokes number will be low. And then when it's actually, if you see that Stokes number is directly proportional to d square. So if the particle size varies with the particle size square, square of the particle size. So diameter is very important. So if you have more the diameter means more the Stokes number. So smaller diameter means smaller particles, they will be actually reflected, they will be not coming on the impaction plate. And this impaction usually has kind of grease, and that grease is used to because this particle can be bounced back again, but when you have grease things, so it will be just stick with that one, so that will not come. Smaller particles follow the streamline, avoid contact with the planes, okay, and they exit the impactor, resulting in a size selection, size distribution with mean diameter larger than the original one. So this is how the impactor works. So for example, if I have to select this one, select PM 2.5 or PM 10, I have to remove particles more than PM 10 if I have to collect PM 10, okay. If I have to collect PM 2.5 means I have to remove particles more than 2.5. So the diameter of the size, nozzle size, and then velocity, impaction velocity, this becomes very important, okay. And this is the equations, you can just see this one. Rho is the density of the particles, dp is the diameter of the particles, u is the flow velocity. So velocity is very important, Stokes number is directly proportional to the flow velocity, okay. Cc is actually Cunningham factor because of the particles that can be attached during the transport. Then mu is the gas or air, viscosity of the air, and W is the diameter of the nozzle. So if you see, if you increase, as in the previous lectures I was discussing, if you increase the diameter size, Stokes number will be increasing, and when the Stokes number will be increasing, Stokes number will decrease. If you increase W, then Stokes number will decrease. So you cannot be will be able to collect the particle of desired size. Then one more important component is actually denuder. This serves to remove gases while passing 95% of the filters. So almost like it depends that how much particles you want to collect on the filters, okay. So usually this is actually collection efficiency we call it, and denuders are usually served to remove gases while passing 95% of the particles. To help, they allow the particles. I think in the previous lectures I said denuders, so remove the what you call humidity. Is not for the humidity, it is for the to remove the gases, some of the gases. And various types of denuder are tabular, parallel plates, or annular, honeycomb, and cloth kind of things. Gases diffuse to the surface of the denuder. Often a coating is applied to retain the specific gases. So you can, and that gas, when it is actually retained, you can use for the analysis, okay. The question that you should ask, that why do we want to remove the gases, okay, because this becomes very important. Now what are the factors that can be affecting our sampling system? So this is very important, and one is actually on the deposition in the inlet. So in the inlet, if your inlet, because when you are continuously doing the sampling, there will be particle that will be deposited on the inlet itself. So the diameter of the inlet can change, and when the diameter of the inlet and then characteristics of the flow can also change during this one. So this can happen during the deposition, during the transport or storage, and agglomeration of the particles can happen because of that one. During, we have to actually, if there is a more evaporation of the particles or condensation of aerosols, then this can also affect our sampling. Re-entrainment of the deposited aerosols, this can also, all of these factors should be accounted for so that measurement can be corrected and to ensure the accuracy. So for example, in the first one, deposition of the inlet, what you have to do? You have to clean the inlet. You have to keep on cleaning the inlet. You just cannot, once you brought the sampler, it is not that you can just use the sampler for long, until its life, so, okay, or for say 10 years. You have to clean that one, and you have to pack your samplers, and then especially the nozzle ones. Otherwise, if there is a deposition in the nozzle, then also that can affect. Okay. Sampler extraction. The withdrawal of the aerosol from the environment required making particles enter the sampling system. If they don't enter the sampling system, they will not be collected. The efficiency at which this is done is called inlet efficiency. So this means all the particles, so they have to come to the sampling system unit, but all the particles will be coming. So we need to provide the specification about the inlet efficiency. So this means inlet efficiency, we know that efficiency cannot be 100%, so this means this will be reduced. Okay, and it depends on the ambient gas velocity, what is the velocity with which we are actually doing. Then inlet geometry, this is very important, the size of the inlet and then position where it is actually, the sampling gas velocity. Okay, so there are two velocities, ambient gas velocity and sampling gas velocity. Ambient gas velocity means the wind speed itself, and then sampling gas velocity means inside that one, and then particle aerodynamic diameter. So sampler extraction becomes very important for this one. And then this is last one about this one, like I have been discussing that your sample should be actually like isokinetics. What is the meaning of the isokinetic? Iso means same, so this word is actually iso means same, and then kinetics means flow, actually you can say here. So for example, if there is actually wind that is coming, actually gas here, okay, the nozzle has parallel with the gas flow. Here the nozzle and then sampling probe, for example here sampler faces are here, so the nozzle is parallel. Okay, it is not actually here, the sample velocity is equals to the gas velocity here in this period. So this will be homogeneous or isokinetics. Okay, but if you see on the top one, this actually air is coming here and then it is deflected like this little bit. So here you will not have actually kind of isokinetic. So it's just imagine a situation like in the river, when the river flows, the kind of main stream, the sides, what do you call, river sides, the water will be flowing at a different rate, but inside that one the water will be flowing at a constant velocity or relatively same, so middle of this one. So we should have the knowledge of isokinetic energy, isokinetic effect. So I do not discuss much of these things here because it becomes very important that this is actually designing and then civil engineering part, how you have to maintain this one. But yes, you should have some idea that what is the isokinetics and how it works. So sampler, if it is not isokinetic, your sampling will be disturbed. So with this, I think I have completed this part of aerosol sampling. What are the requirements, what are the different sampler types, and how we can avoid, what are the sample consideration, or what are the factors that can affect the sampling itself. So I will stop here, and in the next lecture we are going to discuss very important topics. What are the different types of filters that we are going to use for this one. So thank you so much.